Thank you for joining us on Synthesis Workshop. On today's Research Spotlight episode, we're joined by Dr. Mark Walsh. Mark got his bachelor's degree in chemical and pharmaceutical sciences from Dublin City University, where he worked on sulfur-based organocatalysts under the supervision of Dr. Emma Coyle. He subsequently completed his PhD in the Kitching group at Durham University, where he investigated methods for the enantioselective synthesis of ammonium cations. Currently, he's a postdoc in the Clayton group at the University of Bristol. And with that, I'll hand the floor over to you, Mark. Thank you very much for coming on today.
Hi, and thank you for having me on the show. Today I'm going to be talking about the main bulk of my PhD, which is this recently published work on the enantioselective synthesis of ammonium cations, which I conducted under the direction of Matthew Kitching at Durham University. So nitrogen stereocenters, the most common one is these tertiary amine species, which are conformationally unstable. This is due to this interconversion, which can happen due to the quantum mechanical tunneling of the lone pair, which inverts the molecule upside down. And for ammonia, this inversion is extremely rapid and can occur about 30 billion inversions a second. And it's only in special cases such as electron deficient aziridines or so, which will allow for any sort of conformational stability in these species. So the next case is these bridgehead species, which you will notice are most prevalent in the cinchona alkaloid species. However, for this backbone to be chiral, you need to have other stereogenic centers to desymmetrize that threefold symmetry. So these are conformationally stable because you can no longer have the lone pair inverting into the ring, and so they are locked. The last case is the quaternary ammonium salts, in which you have the lone pair locked in this covalent bond now, and so it can no longer invert. And these are configurationally stable and easy to synthesize, and they can be the only stereogenic element in the molecule, unlike in the bridgehead species. And because of the ease of the synthesis and their special solubility properties, they have found ubiquitous usage in industry, academia, and domestic purposes. And they have found the role of phase transfer catalysis, surfactants, as organocatalysts, as MOF templates, and in some pharmaceuticals as well. So accessing these nitrogen stereocenters can be quite difficult. And the first case of it, which is the proof that it can indeed be resolved and can be chiral, is the case of Peachey in 1899, where they did a fractional crystallization using camphor sulfonic acid on this benzylated ammonium species, which they then replaced the camphor sulfonic acid with the iodide again, with potassium iodide. Work by Havinga and then followed up and later studied by Kostyanovsky focuses on the spontaneous resolution process where this ethyl methyl allyl aniline salt under chloroform conditions can crystallize as a conglomerate and then can be spontaneously resolved, much like the Louis Pasteur experiment. But really the main goal for synthesis would be to have an asymmetric variant where you can have an enantioselective synthesis, where you can set the stereocenter predictably without the need for a resolution process to be occurring. But this is yet to be achieved. So as a retrosynthetic analysis, how would this occur? So we propose that you would have to have these three conditions to be set out in order for this to be achievable. So first of all, you'd need to have a recognition event to stabilize one of the enantiomers in solution. Then you'd want to have a racemization event, which would then convert your undesired enantiomer into the correct form that you'd want. And then finally, what you'd need is conditions where you have the recognition and the racemization working together in the same pot, so that as you're recognizing and stabilizing one enantiomer, the unwanted enantiomer is then being funneled towards to be recognized and stabilized, which then, at the last case, would then give you an overall majority of one enantiomer of the other. And so the bulk of supramolecular chemistry has been tackling this recognition problem for quite a few decades. So the origins of supramolecular chemistry finds itself in ammonium recognition, especially with the recognition of crown ethers and cyclodextrins with protonated ammonium cations. Later work has shown that you can also build these complicated host species to accommodate the ammonium species within them, or to hydrogen bond to them selectively from solution. It was the work by Toda that really was quite remarkable though, because rather than having to construct a very rigid set host, you can have this bienal species recognizing an ammonium through this beta hydroxy species, which hydrogen bonds to the counterion. Tayama and co-workers then built on this work by using not a silicon alkaloid, but just a more stripped down version of a beta-hydroxy ammonium salt, which then showed the same hydrogen bonding motif to allow for the recognition to occur. We proposed, however, that we could get a more direct recognition of ammonium cations, especially from reading the work of Chris Hunter, which shows that these alpha CH bonds are quite acidic and have similar hydrogen bond properties to hydroxyl group themselves. And so we proposed that we could potentially get a more ubiquitous recognition using an unfunctionalized ammonium species, as drawn here. So when exposing this racemic aniline salt with both enantiomers of bienol, with half an equivalent as a resolution process, we found that it formed a solid precipitate in 71 to 74% yield. From this solid precipitate, we could grow single crystals, showing the asymmetric unit on the slide here, which then we could recover the enriched ammonium salt using a simple ether water aqueous extraction. We were also able to use the crystallographic analysis to identify the configuration of each ammonium stereocenter from this process. The final question then was, how can the enrichment be measured? This is a problem because HPLC methods haven't been developed for these ammonium species simply because they have never been synthesized before. And so we could not find any HPLC conditions that were suitable for the resolution of these enantiomers by HPLC. So we turned to the work of Jerome Lacour and his co-workers, which used these non-lanthanide chiral shift reagents. Firstly, we used trisfat, which is a commercially available chiral phosphorus species. It's fairly expensive to buy and is difficult to actually synthesize and resolve yourself. We also found that although it had some resolving power, it had poor substrate scope. We also turned to this binfat species, which is not commercially available. However, you can produce it yourself from a two-step synthesis on multi-gram scale. This showed good resolving power, good substrate scope, and also good solubility properties, which is important as well. We finally also found this bis binaphthol borate species, which we nicknamed Borbin, which again is not commercially available, but is very straightforward to synthesize in one step and can be produced on multi-gram scales in nearly quantitative yield. This has excellent resolving power, however runs into some problems with solubility with some ammonium species. And here we see some of the crystal structures that I have produced just to confirm this configuration of the centers. So moving on to the chiral shift NMR now. At the top we have the racemic ammonium bromide salt just as a standard, and I've highlighted the peaks of interest in purple which designate the racemate. When exposed to trisfat, we see that there's only one peak that really shows any separation at all. There is poor resolution of this salt and was deemed unreliable for the entire process. The second example shows Borbin, which shows much better resolution power for some of the peaks. However, as mentioned previously, this suffers in solubility, and many of the ammonium substrates that we attempted to analyze with this failed due to crashing out from the solution. Finally, we have binfat, which has the best of both worlds. So it has good solubility properties, it has good resolution of the enantiomers, which is shown in the pink and blue, which then means that we can have clear integration and clear enrichment measurements. So here we have an experiment showing the racemate on the top, where you can see the 50-50 mixture between the two enantiomers, and then the resolved material that was resolved earlier. We can show that we have now a reliable method for measuring the enrichment, which at this species was measured at 9010 EOR. We also turned to screen other possible recognition species. So we took some commercially available 3' substituted bienols, some 6' substituted bienols, this amine substituted binaphthol species, crown ethers, some tartrates, some tartrate esters, calixarine, and these tadol and spinol variants as well. The ones highlighted now were the ones that showed any solution phase recognition occurring with this ammonium bromide species. Strangely, the 3' substituted bienols don't show any recognition at all. We suggested that this is possibly due to the steric hindrance next to the hydroxyl groups, which then can interrupt the hydrogen bond network from forming. Some species, such as the spinol and the octahydral binaphthol species, have yet to be isolated as solid complexes, although they do show solution phase recognition occurring. We, however, resorted to sticking with bienol, since it is cheap, commercially available, and showed decent recognition on a wide scope of ammonium salts. This scope can be shown here, and we can see that we can go from some poor examples to some excellent examples in recognition. We have discerned that the steric bulk on the ammonium is very important for the recognition efficiency. So the first example with the ethyl ammonium species, we have poor recognition occurring mainly due to the lack of steric bulk on that ammonium species to differentiate between the two enantiomers. However, when using a more sterically bulky substituent such as the isopropyl group, this recognition is upgraded then to an 80-20 Dior. We've also shown that when you have a 80-20 Dior, you can then subject it to a recrystallization process to upgrade the enrichment. Some substrates, such as the isopropyl allyl iodide salts, showed greater efficiency in the recognition process, as did the benzylated species, which was able to be enriched into 96,4 Dior in the ternary complex. We were also able to recognize the indolinium species shown below in good to excellent Dior. We are also able to obtain single crystal X-ray structures for all the substrates in the scope in order to confirm the configuration of each stereocenter that we had resolved. Due to the commercial availability of both enantiomers of binyl, we were able to use the S-binyl to also resolve the opposite enantiomer of the ammonium species. This was done in order to validate our method by having comparable yields for each substrate with the opposite enrichment, and also to confirm that the opposite configuration existed for each of these ammonium stereocenters using the opposite enantiomer of binyl. Each of these ternary complexes are highly crystalline and so are perfect for analysis by X-ray diffraction. Here I've shown a number of crystals that I had grown in the lab, normally from methanol or ethanol, which were then perfect to analyze by X-ray crystallography. From our X-ray crystal studies, we were able to find a general structure for these ternary complexes and how they form. In general, we have a binyl to bromide or iodide chemterine network, which forms a backbone, which then encompasses around the ammonium species as a chiral network. This then selects one of the enantiomers preferentially over the other. So here we have the asymmetric unit of one of our salts, which then, when expanded, we can highlight the binyl to bromide network as this van der Waals surface shown in teal, which then also shows the ammonium cation species within the pockets of that network. We synthesized both the matched and a mismatched product. So the matched product being the selected form from the initial recognition species. So in this case, we have this S-ammonium species complex to an OR binyl. From a single crystal, we have a Z prime of 1, a melting point range, density, and energy values were calculated. Then taking that same ammonium cation, but exposing it to S-binyl instead, made the mismatched diastereomer product. When single crystals of this species were grown, we noted significant differences in the Z prime, which shows a higher Z prime number of 2, which is indicative of an awkward packing structure. We've got a lower melting point, which is indicative of a less stable crystal, alongside of a lower density and lower energy. All of these point to a less stable crystalline form, which is possibly the origin of the stereoselectivity observed in this process. Next, we turned our attention to the racemization step of this process. There's precedent in the literature for ammoniums dissociating in an aprotic solvent, such as acetonitrile, DMSO, chloroform, and DCM. It has also been shown that both heat and iodide catalysts can promote a dynamic exchange mechanism. If the salt is then put into a dynamic exchange, as shown in the scheme here, it would then racemize in solution during the complexation and would then allow for a dynamic resolution to occur. So in this scheme, we show a racemic ammonium bromide salt in the presence of heat and an excess alkylating agent, giving this mixture of 1-to-1 salt to aniline species in the endomere. When performed on an enriched ammonium salt, we can observe the decay in the optical rotation of the sample over time. This was heated in the presence of excess alkylating agent, in this case it was benzyl bromide, so as not to fully dissociate the ammonium salt. When this substrate was exposed to these conditions, we observed full decay in optical rotation in 425 minutes. Next, we sought to combine these two processes together in a single pot. So firstly, we have this tertiary aniline then exposed to an alkylating agent to form the racemic ammonium bromide salt. This ammonium bromide salt is then exposed to binyl in the presence of heat. Initially, a precipitate is formed, which then gave us a 74% yield and an 80-20 Dior for this ternary complex. We also analysed the solution phase of this experiment and show that we have an 11% yield, which is also biased towards the same configuration. And below is a picture of the precipitate which was isolated from this experiment. And here I show a general scheme and the scope of this enantioselective prep. So in a one-pot process, you can start off with a tertiary aniline, which then you expose to an alkylating agent and an enantiomer of bienol at 50 degrees. And after 48 hours, you can isolate the ternary complex, which after a aqueous workup, you can extract your ammonium salt. So this process can isolate ammonium salts in good to excellent selectivities, and because of the commercial availability of both enantiomers of bienol, we've shown that we can also synthesize both enantiomers of every ammonium substrate. Next, we sought to monitor the enrichment over time for this process. So taking this isopropyl aniline and exposing it to benzyl bromide over the 42 hours of this experiment, we monitored both the yield and the selectivity of this process. These substrates were chosen because they had no extra hydrogen bonding functionalities. They were amenable to both the racemization and the recognition conditions, and they had sufficient steric bulk to be selectively recognized by the bienol species that we had used in this process. We can see that there's a rapid rise in the enrichment of the species, which then eventually plateaus at about 96:4 EOR. The yield similarly increases, but at a slower rate, until it plateaus at about 30 hours in. The shape of the curve indicates that there may be a thermodynamic process responsible for this selectivity, as distinct from a kinetic resolution process, where you'd be expecting the enrichment to be decaying over time as the resolution is occurring. Instead, this process shows that the enrichment increases and then reaches a steady state. We have also proposed some selectivity rules based on steric considerations of the substrates that we have found so far. When you put the largest group and the smallest group coplanar, then you will have the next largest group in the proximal position, so it would be pointing up above the plane of the molecule in the case of using the ore-bienol complex. And the same for when you have a ring system, such as the indolinium systems. You put the largest ring system coplanar with the ring, and then you have the medium group appearing above the molecule. Next, we wanted to demonstrate the importance of a nitrogen stereocenter in a supramolecular process. Commonly, we use the cinchona alkaloids, such as synchonine and synchonidine, which are pseudo-enantiomeric to each other. And luckily, in many cases, you have opposite senses of induction when you use these pseudo-enantiomers. However, you cannot assume that this will always be true, and only with a true enantiomeric relationship will you always guarantee opposite induction. So when using a synchonidinium-based salt, you can resolve a racemic bienol mixture, and it selectively recognizes the ore bienol in 8 to 92 EOR. Synconium version of this recognition process too pulls out the ore bienol species in 85 to 15 EOR. However, when true enantiomers are used in this process, you can use the S enantiomer of our salts to pull out ore bienol in greater selectivity than the cinchona alkaloids. And because of our ability to synthesize both enantiomeric forms, we can use the opposite enantiomer to pull out the S bienol species from the racemate, which is impossible to do with these pseudo-enantiomeric cinchona alkaloids. Next, I just have a small video to show what the Onepop process actually looks like in the lab. So here I'm adding in the aniline, some chloroform, and next I'm going to add in the alkylating agent, which in this case is going to be allyl bromide. Then I seal it, and I place it in the sandbath to heat for a few minutes. This is to do a kind of a pre-induction step so that it has some of the alkylated form in solution, so that when I add in the bienol, it has something to recognize. So right now it's alkylating the aniline salt into the racemate, and here I'm adding in the solid bienol, which is then sealed and left to heat. You'll see initially that it doesn't fully precipitate out, it actually goes into solution first. Then that recognition event occurs and it forms a white precipitate, which is then slurried in the chloroform mixture for 2 days. As it slurries, it's then going through these equilibria. So it goes through a complexation event to form both the matched and the mismatched pair, which then, because of the heat, preferentially dissolves the less stable crystalline form of the mismatched pair, which then brings the ammonium salt back into solution where it can racemize and then it can be recomplexed to form the favored matched pair. Once it forms the matched pair, it's less likely to redissolve and to undergo this racemization process again. So overall, you have a bulk mixture which is biased towards one favored matched crystalline form. And so finally, I'd just like to say thank you for listening to my talk, and I hope you enjoyed the work that we had conducted. This is all due to the guidance of Matthew Kitching and the help that I had with Joseph Phelps and Mark Lennon, and also from our crystallography expert, Dr. Dimitri Ufit, who lent his expertise to all the crystallography that you've seen previously.
Thank you for tuning in for this Research Spotlight episode, and thank you to Mark for a great talk. If you enjoyed the episode, you can support us by subscribing and telling your peers about this podcast, and feel free to send us any questions or comments you have. Follow us on Twitter to stay up to date, and see you all next time.